Hi, and welcome to the fifth installment of the MG Chemicals webinar series. Today we're going to look at RTV silicones. Now, MG Chemicals does not produce these materials. These are a product of Momentive Performance Materials. MG Chemicals is a master distributor for these materials, and we've mentioned them in prior webinars. Specifically, we go back to potting and adhesives. We did mention RTVs, but really the portfolio that we have is too expansive, and we felt that it was appropriate to dedicate an entire webinar strictly to going over the products that we have to offer. So with that, let's get started. So on today's agenda, we're going to look at silicones versus our other resin chemistries. And again, we've done this before, but just as a refresher, let's look at some of the pros and cons that come with silicone materials versus some of the other resin chemistries associated with both adhesives and potting applications. And then we're going to break down silicone chemistry itself. We're going to look at the different types of silicone. And then the third point I have to make here, modulus, is something that I brought up in the past, but I really want to accentuate and help you to sort of illustrate and visualize what the concept of modulus is. And this will be important for certain applications, maybe where an engineer is deviating from just describing a material as hard or soft, and they're getting into the idea of modulus. So I think it's important to cover what that actually means. Next, we'll look at some of the specialty grade materials. So we'll start with thermal management. And in that, I mean thermally conductive materials, materials that can move heat away from components. Next, we'll look at the optical grades, some low outgassing materials, and then finally, we'll go over examples of how you can systematically go over, ask the right questions, get the necessary requirements in order to filter out all the options and choose the right product. Okay, so starting with silicones and other resin chemistries. Okay, so if we start with polyurethane and we look at the temperature range, what we note here is that typically your operating temperature varies from about -50 Celsius to 125. And that 125 is really sort of the weak point in terms of polyurethane overall. They're otherwise very versatile materials, but they really don't have the high temperature resistance that's demanded in a lot of applications. So with that tends to be one of the weak points in polyurethanes to rule it out. Now, when we talk about modulus, again, we're looking at relatively how easy something is to stretch. And with polyurethanes, we sort of get both ends of the spectrum. They can be made very tough and rigid, or they can also be made very soft and pliable. So it's kind of runs both ends of the spectrum there. Chemical resistance, generally speaking, is pretty good. And again, there's a spectrum within polyurethanes themselves. But if you want to try and classify the overall family of materials, generally speaking, it's pretty good. They hold up pretty well to a wide variety of solvents. Okay, so now the same comparison looking at epoxy. And with epoxy, again, we see a little bit higher in terms of the upper operating temperature, typically around 150. Now that's not hard set in stone. You can see some with very high glass transition temperatures up to over 200 degrees Celsius, but your typical bisphenol A type epoxy material will usually be good up until about 150 degrees Celsius. And with the modulus, these tend to be very high modulus materials. They tend to be very stiff, not a lot of deformation or stretching, compression, that sort of thing. But chemical resistance, that tends to be superior, and that tends to be one of the sticking points when people are looking at an epoxy material. If it's in a particularly harsh environment, you may seek that high cross-link density you get with epoxy. So that tends to be one of the strong features of this kind of chemistry. And then finally, when we look at silicone, well, that tends to be a case where the operating temperature is sort of enhanced over the other chemistry options. Typically, it's about minus 60 to 200. But again, there's some materials that range from about minus 115 Celsius to up over 300. So that tends to be where it is most likely used when you have that higher temperature or just a wide operating temperature demand. Silicone tends to be, a preferred material here. With modulus, again, it tends to be a lower modulus material, and that is advantageous in terms of stress relief. So if you have delicate components, if you have applications with thermal cycling, and you want a softer material that's not going to exert nearly as much stress, you may want to use a silicone. But again, one of the drawbacks here is not nearly as good chemical resistance, generally speaking, when we compare it to the other families. There are some grades that hold up reasonably well to some solvents and oils and stuff, but generally speaking, it's a weak point of silicone materials. Okay, so now let's look at the different types of silicone materials that you can get. Okay, so basically these break down into the type of cure mechanism as well as whether it's a one part or two part. So we start with a one part condensation cure. And with this chemistry, basically it is ready to go. It is the preferred type for a lot of adhesives. So these are room temperature curing type materials where the mechanism of cure is atmospheric moisture. So that's why that water molecule is pointing towards the outer edge of that blob that's illustrated there. It is the moisture that is available in the environment of where the silicone is applied. And then conversely, we also have a two-part condensation cure. So that's one where you would add the catalyst to the resin, whereas the one part, the catalyst is already added. It's already pre-mixed. With the two part, you do have a little bit of latitude in terms of not only how much catalyst you can apply, which does to some effect influence the curing behavior of the material. But you also have some latitude as well as what catalyst you can use. And again, there's one part addition cure. So with addition cure, these are materials that can be accelerated usually with heat. Okay, so you don't have that choice when you're talking about a condensation cure. And that's one of the drawbacks that a lot of people steer away from when they look at silicones. When it's a condensation cure, there's really not a lot that you can do in terms of speeding up the overall cure. You can try and make the atmosphere very humid, and that has some effect, but it's still going to lag in terms of other chemistries where you can simply hit it with a lot of heat and cure a part in under an hour. So with a one part addition, again, we have the catalyst already embedded within the material, and you can heat it. A lot of these will cure at room temperature, but you can accelerate that cure by adding heat. And then finally, the two-part addition cure, and these tend to predominate with the potting materials. So again, that's where you add the catalyst, and typically the catalyst ratio is fixed here, and it's a specific catalyst. So you don't necessarily have the latitude and freedom to choose whatever catalyst you want as you do with the condensation cure. So again, just to summarize, with the condensation cure, they react with the atmospheric moisture. So it's a passive cure, and that can be advantageous if you don't necessarily have heat curing equipment. But you do have to keep some certain things in mind. With the one parts, you get reaction byproducts. So this can be anything from alcohol to acetic acid, in which case your substrate type has to be considered. And the other thing here is the depth of cure. And that's because what happens is the outer edge cures first. So if you form that tough skin, that in fact acts as sort of a boundary that prohibits any further moisture from curing. So you can't cure these condensation cures, you can't cure them if they're made too thick. Whereas with the addition cure, again, they do not require moisture and can be accelerated for heat. So that would be more ideal if you're looking at high production, because you can have a more direct influence on the throughput time, as well as we don't have the constraint of the depth of cure with these materials. They can be applied very thick. So again, as I mentioned before, they tend to predominate in terms of potting materials. Okay, now I want to look at the concept of modulus, which we have talked about before. So again, if we look at this illustration, what I've done here is I wanted to show that, okay, if you have two materials that you could stretch to the same distance, and let's say they were to snap at that distance that we've pulled them apart. Well, with modulus, it's a case of the destination is really as important as the journey. So basically, it's a ratio of the stress over strain. So how much stress did you need in order to deform the material that much? And when we say stress, we're talking about effort to pull something. When we talk about strain, strain is the actual plastic deformation. It's the stretching of a material from its initial state to a secondary state. And so here, if you are exerting more stress in order to stretch a material the same size, you would conclude that here, no, the modulus is not equal. In the bottom example, where the two tractors are kind of struggling to pull that material, that would have a higher modulus than the case of the top example, where it seemed to be the tractors move a lot more smoothly. Okay, so now that we've gone over some of the preliminary theory with respect to silicones, now let's look at some of the specialty grades that MG Chemicals offers. So let's start with thermal management. Okay, so we've seen this before where we are trying to bond a heatsink onto a CPU. So with traditional materials, you will get reasonable thermal conductivity. But with silicone materials, what you tend to get is a much higher degree. And that's what I'm trying to show here when the heatsink sort of glows red. That's meant to show that that heatsink is getting hot, so the adhesive is more efficient as a thermal conductor. And that's true if you compare thermal conductivity values. With epoxy, even the best products on the market, you might be pushing 3 watts per meter Kelvin, whereas with silicones, we're typically in the range of 5 to 10 watts per meter Kelvin. So they are superior materials, not only if you need something of lower modulus, but if you just need a whole lot more thermal conductivity, those silicone gap fillers are really superior materials in that respect. So here we have a bunch of different products. The TIA 350R is a 1-part potting material. And again, we see thermal conductivity around 3.5. Whereas the next 3 materials are gap fillers. So a gap filler basically cures to a soft putty. It's not really an adhesive, but what it is it's meant to conform to that interface between the heatsink and the component that you're bonding to. And usually you can actually just peel it off if needed for repair. So don't think of it necessarily as an adhesive, but it will hold. But again, they tend to have very high thermal conductivity and are very conformal. And then the next 2 materials you see, the TIA 208R and the TIA 260R. Again, those are potting materials, lower viscosity, so they can fill a void, and they are addition cures, so there's no limits in terms of the depth of cure. And then finally the TIG 210BX, and that's a non-bleeding grease, meaning it doesn't easily separate in terms of the filler and the oil. Okay, so that's thermal management. Now let's look at the optical grades. So with the optical grades, let's look at an example like if we are trying to bond a screen onto something like a tablet or a cell phone. So what we need is a material that is typically very soft, almost like a gel material, and that helps in terms of facilitating the constant movement and compression that would come with bonding a screen. So when you bond a screen, let's say it's a touch screen, you're constantly tapping it, so it needs to accommodate that constant compression, as well as there's a lot of lateral movement in terms of your finger swiping and things like that. The other main requirement here is that it's optically clear. You want something that allows a lot of light, is very see-through, in other words. So again, a lot of materials, but again, typically these are either addition, or there are some UV cure grades if you have throughput concerns. But again, the main thing I wanted to highlight here is the percent transmission. So that's how much of a specific wavelength of light is able to get through. So you see it's greater than 99%. That just means it's a measure of how clear a material is. And these are adhesive materials. So again, we see them a lot for screen bonding and things like that. Okay, and the last specialty grade item I want to go over is the low outgassing materials. Okay, so with low outgassing, I want to bring up the standard that's typically referenced, which is ASTM E595. And for that test, what we're doing is we're measuring the amount of off-gassing of material that's kept in a chamber for 24 hours, and the test conditions are 125 Celsius and about 10 to the minus 5 torr of pressure. So they put it under vacuum at a very high temperature. And then basically what they will do is connect it, and you're looking for two things here. You're looking for how much off-gassing that material accumulates over 24 hours. So that's typically just a before and after weight measurement. But the other thing here is that they'll attach this condenser apparatus, and some of that outgassing material is then condensed, and they measure the amount of volatile material. So that's how much material sort of condenses from that off-gassing. And the NASA standard is if the total mass loss is less than 1% and the collected volatile condensed matter is less than 0.1%, then that is considered low outgassing per the NASA standard. So this is typically the benchmark when you're recommending a material that is low outgassing. And again, several products here. Most of them are adhesives. Okay. So again, the thing I wanted to highlight was the total mass loss and the CVCM, which are the critical things that you would communicate to a customer in terms of selling them on this idea that it is low outgassing material. I brought up color because sometimes that could be important, but that's usually a sort of a secondary consideration. The last three materials on the right, again, those are gap fillers. So not necessarily a material that can strongly bond something. It cures more to a putty consistency that you can usually easily tear off. Now these three materials are also thermally conductive. So that's sort of an added bonus if you have a potentially, pretty rare application where you need both, but that is available. Okay, so we've gone over the specialty grades, but what about the non-specialized grades? How do we go about gathering all the requirements, making sure we ask the right questions in order to choose the right material? Okay, again, we've looked at various properties, but we sort of draw it into, and I've condensed it down here to sort of four considerations, main considerations. And the first one we're going to look at is processing. So processing, you got to consider what we talked about before when we looked at the different silicone types. We looked at 1 and 2 part, and we looked at condensation versus addition cure. Okay, so typically 1 part products are preferred, and that's pretty easy to explain. Obviously, they're much easier to use. There's no measurement required. There's no mixing required. So again, this is sort of ready to use, idiot proof in a way. Now condensation versus heat cure, well, we sort of went over that as well. Condensation cure is passive cure. Provided the environment is not too dry, you simply apply it and let nature take its course. So of course, it does take quite a long time, and there's very little you can really do to influence and speed up cure. So that has to be something to consider versus an addition cure where you can have more of an impact. So again, if high throughput is more desirable, you might want to look at something that's an addition cure, where you can in fact speed up the cure. The other thing too, of course, is part geometry and section thickness. So with the condensation cure, we have to consider that these are not suitable for potting. And again, typically you're potting between, an inch, 2 inches. Well, that's not going to cure all the way through, and that's going to have a massive effect on the final properties. And of course, the other thing too with the condensation cure as a byproduct, so one of the byproducts, for example, is acetic acid. So it's not recommended if the adhesive would be applied onto a metallic surface that you would choose a material that has acetic acid as one of its byproducts. You would choose something that releases something that's far more neutral, like alcohol, for example. Okay, when we talk about consistency, that is just a gauge of the viscosity. So it sort of depends on the application, but it also depends on the relative orientation of the substrate. So if you think about potting, you would need a material that is going to wet out over a surface. You want something lower viscosity, and we do provide values for viscosity, but you can almost just take it generally as flowable, non-flowable. So in this case, we got a material that is flowable to wet out a surface. The other consideration if you were using an adhesive is, are you bonding a horizontal surface? So again, that might be a situation where you'd want something a bit more lower viscosity so it wets out that surface and it covers the surface area a little better. Conversely, if you're bonding something on a vertical component, well, in that case, you don't want a material that's going to sag. You'd want something that's more of a thick paste material. So again, proper question is, okay, give me the orientation. Is this going to be applied vertically, horizontally, that sort of thing? And then we look at, again, something, this is more of a, I would say, a secondary consideration. But more broadly speaking, we can call this term the toughness. And again, we think of silicones as soft materials, but there is still a spectrum to consider. We have materials that are extremely soft gels versus materials that are maybe not semi-rigid, but fairly stiff and hold their shape quite well. So if you're looking for a stiff or a harder material, something with a higher tensile strength, that could be something that is ideal for strain relief. So if you think about flex cables, flex cables are something that need to be flexible, but you couldn't choose a soft material. Otherwise, you're really not offering the cables any strain relief themselves. Every time they flex, all the strain would be on the cables. So you might want to choose a stiffer material that acts as an intermediary for that strain relief. Mold making is another one, and that's because if you want to make a mold, you want something with high accuracy. And mold making materials tend to have very low shrinkage. They tend to be stiffer and harder materials. And then finally, if you're doing potting, and that could go either way, but with potting, typically you want harder materials in terms of providing more impact resistance. Whereas with soft materials on the other end of the spectrum, these are more ideal if you're encapsulating delicate surface mount devices. And that could just be if there is any thermal expansion contraction, you want something very soft for stress relief to not exert a lot of stress on that delicate part. And the other advantage is something that's repairable. With the soft materials, you can easily dig them out and remove them in the instance that you need to repair them. Okay, and this last one I just called special considerations. Sometimes these will be more primary considerations, but typically they tend to come out at the end. So with that, I'm talking about things like color. And that can be important, especially if you're dealing with somebody who is using an adhesive along a seam. They may want to have something that doesn't really color contrast the box that they are adhering, so they might have a particular color in mind. Another consideration is their flame retardancy requirements. And we went over this in the second webinar, conformal coatings, where we have some grades that are not flammable at all, meaning if you set them on fire, they do not self-extinguish, versus other materials that are flame retardant. So in the absence of the flame, yes, they will self-extinguish and not carry a flame, meaning the material does not burn. So again, UL 94 is the industry standard in terms of gauging that flame retardancy, and typically what I find is people come out and say if they need that requirement. And then the last thing is there is quite a gradient in terms of upper operating temperature limits. So a traditional grade, which I've done in blue there, typically operates to about 200 degrees Celsius. But specialty grades that I've done on the right, and that's meant to illustrate a grade that has red phosphorus in it. And they can usually handle up to 315 degrees Celsius intermittently. So with especially high temperature demand, that is something to consider. Okay, and then this is just an illustration, a decision tree, looking at 1 and 2 components. So you can sort of see, you know, the different decisions, and it comes down again a lot to processing. With the 1 parts, we need to consider the byproducts, whether it's acetoxy, which releases acetic acid, or if we're using a metal, we want something more neutral curing. And then finally, you know, we look at the consistency. Is it a paste? Is it flowable? And from there, we can sort of say, okay, now we'll look at specialty grades. Do we want high tensile strength? Do we want something that's low outgassing? Do we want something with some oil resistance? So it's not so much the products that I'm highlighting here. It's the stepwise asking questions, gathering requirements in order to arrive at, usually you can get it down to about 1 or 2 different materials to recommend based on these different requirements that come in. Okay, so now let's go over some of the conclusions from today. So again, compared to other chemistries like epoxy and polyurethane, silicones have exceptional latitude in their operating temperature and offer low modulus for stress relief. But again, we got to consider the weak point being that solvent resistance. So that is something to balance with the other requirements. Modulus is the ratio of stress over strain. So again, if we take an elastic band, 2 elastic bands, and we're able to pull them the same distance apart, that doesn't mean they have the same modulus, because one might be more difficult than the other. So remember, it's that ratio of the stress over strain. There are several grades of thermally conductive materials, and these include adhesives and gap fillers. And again, they tend to have exceptional thermal conductivity. Some of them are pushing up to 10 watts per meter Kelvin, which does make them somewhat a superior material over epoxies and polyurethanes. Optical grades offer exceptional see-through visibility. And again, it's for adhering screens where you need that clarity. Several low outgassing compounds are available when needed. And that's for things like high precision instruments, or if you're in a high vacuum environment. So aerospace is very popular, where they may be in an exceptionally low environment and they don't want outgassing during operation. And then finally, we need to consider the processing capabilities, the required consistency, the toughness, along with other factors like flame retardancy, the operating temperature, and color, in order to arrive at the right material. Okay, I want to thank you for your attention. My name is Michael Strong. I am the Technical Support Manager, and we will now open the floor to any questions.